Hi, everyone. Okay, the next topic we're going to discuss is the dynamic Earth. All right, and again, if you can take notes, put them in a PowerPoint, in a Google Doc and send them to me, that would be great. All right, so one of the first persons to come up with a theory about how the Earth worked was Alfred Wegener. In 1912, Wegener, who was a geographer and a climatologist, keep in mind he wasn't a geologist, um, proposed that at one time all the continents were connected in the geologic past to form the supercontinent that he called Pangaea, meaning all lands. And then since then they've been splitting apart. Wegener was one of these guys that just loved sailing all over the earth. Must have been a fun life, and looking and trying to solve all these puzzles that people really didn't have an answer to. And I'm going to explain what some of those are in a minute. Keep in mind, Wegener came up with this idea that Pangaea existed, but he didn't know when. Okay, it wouldn't be for a while until people figured out that Pangaea formed somewhere around 150 million years ago. So let's take a look at some of the evidence that Wegener considered. First thing was he looked at a map of the world, and if you do that, you say, hey, it looks like pieces of a giant jigsaw puzzle. Maybe I can push them back together so that they all connect. Then he looked at the mountain ranges. For example, the Appalachians in the eastern part of North America match up with mountain ranges in Africa. The greater, no, it's called the Lesser Atlas Mountains that are there, and possibly in mountains and also in Scandinavian countries. Wegener also noticed that fossils of the same species can be found on now widely spaced continents. Places like Africa, Antarctica, Australia have the same sort of fossils, namely Mesosaurus, which was a reptile that swam in very shallow water, and Glossopteris, this fern that's found. The question is, why are these same species found on widely separated continents? You would think that deep ocean basins would keep plants and animals from distributing that far. Wegener said it only makes sense if the continents were at one time connected and they could move from one place to another. Then he went to India and he found glacial deposits, but India today is near the equator. Why would you have glaciers near the equator? It's just too hot there. Wegener answered that maybe India was at one time near the South Pole where glaciers formed, and then it slowly moved to the north and slammed into Asia. And then the last line of evidence he had was geologic evidence, coals and coral reefs found at high latitudes. These geologic deposits normally occur near the equator. What were they doing in places like Alaska? It didn't make sense unless they formed near the equator when the continents were at a lower latitude and then moved to their current location. So you would think with all this evidence, almost an unprecedented amount of evidence, that scientists back in 1912 would have said, yeah, great job, Wegener. We think that this is something that we can need to accept. The problem is that they didn't. They had one simple basic question that Wegener had trouble answering, and that was, Wegener, how do you move the continents? They had this idea that, imagine a 1-ton rock sitting on the floor. There would be tremendous frictional forces at the base of that rock. And what would be a force strong enough to overcome that? Keep in mind, Wegener had this idea that the continents were sitting on the seafloor and that somehow they were pushed over the seafloor. Even back in 1912, they could do some basic physics, and they calculated that the force you need to overcome the friction would have been very high. And Wegener didn't have a good mechanism. He said, well, maybe it's the rotation of the Earth that drives the continents. So they figured that out. And they figured the centrifugal force from the rotation of the Earth was simply not strong enough to overcome frictional forces, at the base of the continents. Wegener was out of gas. He did not have a way of driving the continents, and as a result, his theory of continental drift really sort of started to fade away into the distance. In fact, he died in the 1930s, going to his death realizing that many people just didn't accept his ideas. And it's sort of a shame that Wegener didn't make it into the 1960s, because oceanographers started to use sonar to map the bottom of the oceans. And what they found was very surprising. In particular, what they found was that it was very different from what they expected. People had this idea that basically the continents, or I should say the oceans, were very shallow on the sides and very deep in the middle of the ocean basins. It turned out it was the exact opposite. In the Atlantic, you have very shallow seafloor material. In some cases, the seafloor reaches the surface of the ocean, like, for example, Iceland. And then on the sides of the continents, you have the deeper part of the oceans that we call trenches. Why were these features there? Well, back in the 1960s, there was this big research vessel called the Glomar Challenger that set sail, and it started to collect a lot of data on the seafloor. In particular, we found out there were seafloor features like the mid-ocean ridge, the Rift Valley, and the trenches. We found that rocks got older as you move away from the mid-ocean ridge. Why would this be? We found that the hottest areas were in the Rift Valley. That was pretty easily explained. They said, hey, there are underwater volcanoes that are going off, and that's what's creating all the heat in the middle of the Atlantic Ocean. And then there was this thing called magnetic stripes, and I'm not going to get into that in much detail. If you have internet, maybe you want to Google magnetic stripes and seafloor spreading. But unfortunately, I can't discuss it in this video. All right, so Harry Hess in the 1970s finally puts it all together. And he said, Wegener didn't go far enough. Not only the continents moving, but the seafloors as well. The entire surface of the earth is in motion. He said, think of the seafloor like a big conveyor belt, where you basically have hot molten material rising up under the mid-ocean ridge and Rift Valley here. And then as soon as it hits that cold ocean, it condenses and forms solid seafloor material. So you have convection currents that are driving the plates and pushing them apart. And then here, as the seafloor material gets colder, it gets denser and gets pulled into these trench areas. The problem is that we still need more information. Okay, this in and of itself doesn't provide enough to understand the dynamic Earth. And so the latest theory that we have is called plate tectonics. And there are several forces, like I just said, that drive the plates. We have convection currents down here that are pushing the plates apart. We have gravity that's pulling it into the sea, back into the Earth. And the other thing that Wegener didn't understand, but we do now, based on what I taught you last week, is basically it's not solid continents over seafloor material like this. The continents and the seafloor are attached to each other. They form these upper blocks called the lithosphere. And underneath there is the asthenosphere, this sort of soft, slushy sort of material. It's sort of like, the best analogy I can give you is, think back to maybe the wintertime when there's snow and ice on the roads. And I was driving back from Valley View Mall one time, and I had this big SUV Blazer, and I thought, it's four-wheel drive, I can go anywhere. Turned on the radio, and they said that SUVs were skidding off the road just as much, if not more so, than regular cars. And the reason is that if you have low friction below something, it doesn't matter, okay, how big it is, you can still slide over. And that's what it's like below the lithosphere. You have this sort of low friction area, so it glides over the interior of the planet. All right, so it turns out there are 7 major plates. There's the North American plate, the Eurasian plate, the South American plate, African, and Indo-Australian plates. You notice the arrows, okay, that are shown on here. And there are 3 main plate boundaries. Where plates pull apart, we say that that's where plates collide, we say that that is a convergent margin. Where they pull apart, that's a divergent boundary, for example, at the mid-ocean ridge and Rift Valley. And where plates slide past each other, okay, that's called a transform boundary. So convergent boundaries would be, for example, where the Pacific Ocean slams into Asia, or where India is slamming into Asia here as well. Divergent boundaries would be like along the mid-ocean ridge here. And transform faults would be like out in California where we have the San Andreas. All right, so what happens when plates collide? Well, there's a couple of possibilities here. If you have a continent plate sliding with another one, like India slamming into Asia, they have the same density. So basically, neither one can pull the other down into the Earth. And it's like when 2 cars collide. You ever hear of a fender bender before? What happens is they crumple up in that collision zone. And that's what the Himalayas are. It's just where one plate is slamming into the other. On the other hand, if you have an ocean plate slamming into a continental one, the oceanic plate is denser. It's made of basalt, and it will slide down underneath the continental plate like this. As it goes down, it brings water with it. The water lowers the melting point of the rocks, and eventually the rock here will start to rise up and fall volcanoes. Most of the volcanoes on the Earth, all around, for example, the Pacific Ocean, for example, the Aleutians in Alaska, the Andes Mountains in South America, the Cascade Mountains in northwest parts of the United States, Japan, New Zealand, formed by this process of subduction. Now, what do you do about volcanoes that are not near any plates? For example, Yellowstone Park in North America, or even better yet, the Hawaiian Islands. Well, geologists have argued about how those volcanoes form, but we think it has to do with hot spots. We think that there's a large accumulation of hot material underneath the Pacific Plate. Maybe it's a concentration of radioactive material, that's what my theory is, and it burns its way through the Pacific Plate, creating a volcanic island. Then the Pacific Plate will slide off to the northwest like this, and as it does so, it drags those volcanoes with it. And then eventually, once it gets off the hot spot, the hot spots will just form a new volcanic island. Okay, I hope this was useful.